Okay, guys, we continue with our lesson today. Introduction Internet of Things. We are at the end of the week two solo check in but this is the okay. Okay. Two embedded system. First one we can say air fryer. And the second one will be microwave. Okay, so first one would be there is a phase. They will have control panel interface. Heater. They will have heater and they have and they will have gió. I guess yes. Middle I have control what control panel option. Then we have a window. We have turning turning rotate this. Here we will have rotate disk of microwave. Okay, we can put this. Okay, then input a system fryer. Then we have input. Then we have output. Microwave like this. I check. Okay. Okay. Ting 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 ting. Ting 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 ting. Ting ting. Ting 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 ting. Okay, we are correct. way we will have input what code and output. So input push button, then we have the button. Oh, we can have the thermal sensor. Okay. Output we can have LED. We can have heater. Okay. Then microwave will have input. The same will have touch button, rotate button. So yeah, we have also minuter. Yes. Minuter. And we can have timer. Yeah. Call the timer. And then we can have output LED, and then we can have what's more, what's else. My require we can have what else. We can have motor to rotate the disk. That's it. We can have sound, alarm. Okay, here's we can have alarm here. And then we can have here what's else. We can have microwave here. Then virtual. We can have for virtual we can have control panel, virtual audio system, virtual control panel, audio we can have alarm, STIC we can have okay, we make a separate. Static we have touch button, electronic we can have electrical signal, electronic we can have electronic recording, electrical signal we can have thermal electronic thermal sensor, something like this. Okay, do it. Oh yeah. Then to point TC Fitbit charger for okay video feed something electronic input video feed we put on okay we can put something like input touchscreen physical button put display sound display evaluation okay put red drop like this so we don't like so we do like this okay chụp touch bar monitor information about food okay using correct cone touch food they show smart free smartwatch okay everything is okay great job chụp great job here is choosing automatic washing machine automatic teller machine okay automatic ATM teller machine okay good very good digital security system okay audio okay 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 对镜头突突，超级超突突，超级超突突，超级超突突，嘟嘟嘟嘟嘟，嘟嘟嘟嘟嘟。Okay, okay, okay. Okay, 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 okay. Okay, 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 okay. Okay. And we are ready to wait. Okay. Then we can go to with number 3. Okay. Identify the core hardware component most commonly used in IoT devices. Define the interface interaction between software and hardware in IoT devices. Define the role of an operating system to support software in IoT devices. Okay. what makes up the Internet of Things 39. Okay. Shit. Okay.
Module 3 is about hardware and software. Internet of Things devices are built from hardware components and software components working together. So you don't design them in isolation, you design them together to make it more efficient. So we'll talk about these hardware components, software components, and how you partition the behavior of the system. So how do you decide what part is implemented in hardware versus what part is implemented in software? So for instance, hardware is typically used to handle physical interaction, the interaction with the physical world. The sensors and actuators are hardware components typically. Also, hardware is needed to do the dedicated hardware would be needed to do things that are more computationally complex, where software is used to do the control and also slower things, human interactions, things like this. So we'll talk about the hardware and the software and how you design them together. We'll talk about the different types of hardware components that are typical that define these systems. Talk about the software design process too, compilation, interpretation, that sort of thing, and how they come together inside a microcontroller. Now, in more complicated Internet of Things components, you use an operating system. And people are already familiar with what operating systems are, but they mean something a little bit different in the context of Internet of Things devices. So we'll talk about operating systems and talk specifically about operating systems that are appropriate for an Internet of Things component.
Okay. Hardware component.
So this lecture, we're going to talk about hardware and software systems. Internet of Things devices are typically hardware and software combined. So as we're learning about the IoT design process, we really have to think about how you design hardware, how you design software, and how you design them to work together. So you can't think of one in isolation. You need to really think about both together as you're working on the project. So IoT devices are a combination of hardware and software. There's always a hardware part of the design. And you can see that here. We've got a breadboard, and the breadboard's got various components on it. It's got a microcontroller, LED, voltage regulator, capacitors, I see, a bunch of different things, and they're all mounted into this breadboard. One part of this design, one aspect of the design, is the hardware aspect that you can see right there, and that's basically a bunch of components that are connected, wired together in some fashion. Okay, so that's part of the design. And so a designer, if you're going to make an IoT device, you have to think about that part too. In addition to that, that alone doesn't explain what the behavior is. Meaning, looking at that set of devices wired together, even completely understanding what each component does, you can't tell what the behavior of that, right? So you have an incomplete view of the design if you only look at the hardware. In addition to this, you've got to look at the software component of this too. So if you look at the hardware side over there, you've got at the center of it, there's this microcontroller, that big black chip dead in the center. That is a microcontroller, which is the heart of the system. And that microcontroller executes code. And so there's got to be some code, some software, which we can see on the other side of the picture, some software that's going to run on that microcontroller. Now that software is some sample code, and that's actually Arduino code, and we'll get to that later. But there's got to be some software that's running on that microcontroller that talks to all the different components, talks to the LEDs, tells them when to turn off and on, and things like this. So there's this hardware side and the software side, and these things have to work together. You've got to design both of them. So what I mean is when you write the software, you have to be thinking about the hardware. You have to say, oh, I've got an LED and it needs to be controlled in this fashion, so I will write my code this way. You have to be consciously aware of that when you're doing code. Whenever you make a new project, you've got to have a bunch of hardware components, right? You've got to get a bunch of hardware components, wire them together, and decide on that a priori. What are the hardware components going to be? Now, this is sort of a fundamental issue with design projects in general. Things change, right? So at first, when you design something, you have an idea of what the behavior is going to be, and you think you know what the components will be. And then you start doing it, you get into the design, and often you have to backtrack. You might implement something and realize, oh, you know what? I need a different component. This doesn't work for me. So that can happen. There's always that risk. But at the beginning, to start building your system, you are going to have some idea of the type of components that you're going to need. So that's always a trial, right? To figure out which components you're going to buy. Now, you start with a microcontroller, but you need other components around that. And each one of these components has different parameters, different sizes, for instance, and you might care about that. You might need this whole design to fit in a certain space, right? So you worry about the size, different voltage, different electrical parameters, right? How much current can this component take, right? Maybe this LED can only take 20 milliamps, which is sort of common. So if you drive with more than that, you blow up the LED, things like this. So every one of these components has these features that you have to consider before you order them. Now, back in the old days, it used to be, back in the days when I was a kid, when you wanted to do one of these projects, you would go to a store, Radio Shack, which is gone now, effectively gone. You go to Radio Shack, and you could buy the parts. And the people in the store could help you with the parts. So they were knowledgeable about these little parts. So they would say, oh, that chip, it will do this, but this component, this resistor is no good for that purpose or something, right? They have knowledge about the different components and what they did. But those components don't cost a lot, right? Switches and things like that, they're very cheap. So stores like Radio Shack, things like that, they don't particularly care about selling those things anymore, frankly. I mean, they sell them, but it's sort of, they don't make a lot of money off them, I get the feeling. They get to make money off of selling cell phone deals or something like this, something else. So you go to these stores, and generally the people are not knowledgeable about their components, which means that it's on you to understand these components and what they do. So you can't rely, most of the time, unless you go to a good store, and there are stores like that, where you can get somebody who really knows what he's talking about or she's talking about, but often you're on your own. And another thing too is that these type of hobbyist electrical stores, they're rare. They're few and far between these days. You can't find stores that have these parts. I mean, I go to Fry's, things like this, also other local places, but it's hard to find these parts. So often you're buying these components online. You go online, you look at websites. Now these websites, there are a lot of different websites, and they're very complete. They have tons of components. But in some ways, it's sort of a data overload, right? There are too many components, too many slight variations. So you see 100 components that look similar, and you have to figure out exactly the one that you want. And I can't tell you how many times I thought I wanted a component, I ordered the component, it comes a week later, and then it is not what I needed. It is somehow slightly wrong, and now I have to go and order new parts and cycle through that. And it is inevitable that will happen to some extent. So just be ready for that. But you really want to minimize that. You want to be able to know before you go and order these parts. You want to be able to know that they match your needs as well as you can know that. So that is what data sheets are for. So data sheets are basically information sheets about hardware components. And every component has a data sheet. The simplest components, maybe you don't have a data sheet. For instance, a resistor. Actually, even a resistor, you can probably find data sheets. But a resistor is so simple, you don't need a data sheet for that. Okay? They have very few parameters. But any kind of complicated component will have a data sheet that tells you all kinds of information about it: the size, the shape, the inputs, the outputs, the voltage, all the electrical parameters, things like this, all the data that you need in order to use it. So reading these data sheets is really important. You can always find data sheets online. You find the part number, you type it in Google, the part number, type data sheet, and you'll find data sheets. And they can be very complicated to read, but it is important that you be able to minimally read them. Read at least find the important information, just so you can order the parts you're going to need to make these devices that you will be making. Thank you.
Okay.
So we'll continue to talk a little bit more about data sheets for hardware components, specifically for integrated circuits, because they're extra complicated. So right here, we've got this is a rectifier, Schottky rectifier. This is a piece of a data sheet. So if you Google Schottky rectifier, and if you type in the part number for that and type data sheet and Google that, you'll come up with a data sheet, several versions of it actually, and you can click on it, and there are lots of different things inside this data sheet. One thing that you always find inside a data sheet is the physical dimensions of the part, because they always want to tell you how do you build it into a bigger system, right? So how's it going to connect everything? You always want to know that. So this is actually a diagram showing the physical dimensions. It shows all detail, right? The size of it, and actually this is just one cross section. A lot of times these data sheets will show different views from different angles. But this shows you the width of the pins. It shows you every dimension that you need to know about. And actually, right there on the, you can't see all the numbers there. They label them with letters, but there's a table next to it that shows what the sizes are. This is a typical thing you find inside a data sheet. Now you find tons of information in a data sheet, and part of it, certainly when I started, I could not read most of a data sheet. All right, you can read a little bit of a data sheet. Though I don't expect people to be able to read the whole data sheet. And in fact, most of the data sheet you don't practically need. But some key things you should be able to figure out. So for instance, the size, right? You typically want to be able to read the size because there are certain things that you need to know. Like for instance, for this class, when you're say you want to use a breadboard, right? That's commonly what we want to use for prototyping is a breadboard for connecting things. For that, you need to know the size of the pins and the spacing between the pins because the holes in a breadboard is spaced at 1/10 of an inch between each hole. So when you get a component, you want to know that the pins are spaced some multiple of that so you can fit them into the breadboard, things like this. And if they're not, you need to know that before you order the part so you can do something about it. So the physical size, physical dimensions, you always find that in the data sheet, and you'll need to be able to read that. Now, other information, this is a sample of some of the other information in the data sheet. You find electrical parameters and thermal parameters, what temperature can this thing run at. Now, usually, thermal parameters are not something I generally need because I'm not trying to use these components in some extreme environment, but they give some kind of boundaries. Can't be hotter than this, colder than this. That's generally not useful to me, but maybe you're using some application where you need that information. Electrical parameters are important to tell you things like what's the maximum minimum voltage, maximum current that can go through that, and that is actually important because you want to make sure, for instance, that components are voltage compatible. So, for instance, say you get a microcontroller and it's outputting at 5 volts, but you get a component that only accepts up to 3.3 volts, which by the way is a common mismatch. So if that happens, you need to know that so you can either buy the component that matches your microcontroller, 5 volts, or you can do some type of voltage stepping, put a transformer in between, something like that, to change the voltage and make them match. So these parameters, some of these parameters you need, some of them you don't need that much. Now, integrated circuits are another type of component. There are sort of simple components and more complicated components, and the data sheets vary in complexity. So if you look at a simple component like a resistor, and we'll talk more about those later, but they're very simple. Okay, you don't need a data sheet for a resistor or a capacitor. You need minimal information about those components. But more complicated components, the more complicated they are, the denser the data sheet is. Integrated circuits are basically the extreme of that. So integrated circuits, and we've talked about these microcontrollers are integrated circuits. Integrated circuits are chips. Now they're typically made of say silicon based, but they can be made of other materials, primarily silicon right now. And we're not going to talk about the fabrication technology, except to say that they're basically made on these big wafers. So you can see down there, you can see these discs, these flat discs, these circular discs. So those discs are slices of silicon, and you chop them up into little rectangles, and each rectangle is a chip. Right? And so you take that chip and you package it, as you can see over there on the right. You can see the packaging. You hide it inside this bigger package, and the package is used to protect the chip, also to cool the chip as it's running, also to wire its pins. You can see the pins on the bottom. So the pins on a chip are too tiny to contact. So you need them to be bigger. So the package does that for you. So the package provides pins that you can actually make contact with. They're big enough for you to solder into or connect into a breadboard or something like that. So anyway, these integrated circuits, they have data sheets as well. Chips protected by the package. These integrated circuits have data sheets as well, and these data sheets for integrated circuits can be very complicated because what these integrated circuits do can widely vary. And so an integrated circuit, for instance, could be an entire processor, right? And then the data sheet for that can be over 1,000 pages, right? I've definitely seen that. Or simple processors like a microcontroller, maybe you get a 150-page data sheet, right? And it's got tons of information on how this device behaves. Now, most of the time for this class, we won't have to go to that level of detail. We won't have to look at the 150-page data sheet and look at the details of what's going on. In fact, with the components that we're using Arduinos and Raspberry Pis. Those boards, they come with libraries that hide the details for us. Okay, so we will not have to be exploring a lot of the details inside those components, thankfully. But you could. So if you really want to make the most use of these components, these chips, you can look in the data sheet and see lots of features. So the trade-off with what we're doing with Arduinos and Raspberry Pis is that they give us these library functions, and we'll talk about these later, that simplify things for us as programmers. But they hide details, they also hide features. So there are a lot of things that you can't do with a processor, with a microcontroller, just because the library doesn't allow you access to that feature. Now, if you want access to that feature, you can go and look at the data sheet and do it, but you won't be able to rely on the nice, easy library functions that you really want to rely on. And inside this class, we probably won't be going into that level of detail about these microcontrollers at all. We'll just use the library functions and not have to worry about these extreme details of the behavior of these microcontrollers. Thank you.
Okay.
So we're going to talk about microcontroller characteristics right now, the different characteristics of microcontrollers. Now, the reason why this is important for making IoT systems is because when you're making an IoT system, probably the first decision, one of the early decisions about how to implement the system is going to be which microcontroller should you use, right? Now, there are a wide range of choices with microcontrollers, and you're going to have to find one to use. Now, a lot of these decisions are pre-done for you. Like if you work at a company, they use a particular brand, we use Freescale, whatever, that's what you use, right? But even within those constraints, even if you're stuck with, say, you're only using Freescale, there's a ton of microcontrollers you can use, all with sort of different properties and things like this. And you got to pick the one that's right for your project. Because another feature of IoT systems is that they are generally constrained, tightly constrained, okay? So it's not like a desktop laptop, right? If you look at a desktop laptop, those things are over-engineered, okay? In the sense that, you get some quad-core processors running at, I don't know, 3 gigahertz, something like this. Regular user doesn't use that, okay? In fact, it's running at sort of 2% capacity 99% of the time. And so you start playing a game, okay? Certain games, they will suck up that power. They will use what the computer has. But vast majority of the time, that processor is sitting there at 2%, basically idling, okay? Because you don't need 4 cores. You don't need that kind of clock rate. You don't need everything that it has. IoT-based systems, those things are cheap, okay? You want to be cheap. You do not want to buy some big, powerful microcontroller that you don't need. You're always saving money, trying to say, look, what is the cheapest thing that just barely does what I need to do? So what you need is you need to have in mind a set of characteristics that your microcontroller needs, so the bare minimum for your system, and then you look through the data sheets for the microcontrollers to figure out which one has that, just barely, which is the cheapest one that has that. Now, a data sheet, we're not going to look at a data sheet because those are painful to look at, but a data sheet is basically the sheet that has all the information about the particular microcontroller. So if you ever want to look up a microcontroller, you can look on the top of the chip, you can see the name of the microcontroller, its part number, and everything. You type that in into Google, and you say data sheet, and you will come up with a data sheet, most likely. And this data sheet, you might look at one. They are definitely complicated to read. They have lots of different details about the microcontroller. But there's certain information in there, there's certain things in there that we really need to understand in order to make reasonable decisions. So we don't have to understand everything in there, and we will not. But certain high-level characteristics of a microcontroller, you should know what they mean. And so when you look at a data sheet, say the front page of the data sheet, you can at least tell superficially, yeah, it has this, it has that, it has that. That's what I need, or I don't need that, and so on. So let's talk about sort of the basic characteristics of microcontrollers that you might look into. And again, also another thing let me mention is that in this class, you won't be making this decision. You're not going to be deciding which microcontroller you're going to use. In this course, we use an Arduinos, right? And then the next set of course we can use Raspberry Pi. We're set with that. But I'm saying outside of the course, when you want to design your own IoT system, you will need to pick a microcontroller. Okay, so data path bit width. Bit width, what that means is it's the number of bits in each register. A register is a storage element that stores a number. So the bit width basically tells you the size of most numbers in your system. How many bits? So every number is represented in binary as a series of bits, which are binary digits, either 0 or 1. And the more bits, the better. Okay, so what do I mean by that? The more bits mean if you have more bits, like 64 bits, let's say, that means you can get more accuracy than you could with 16 bits, something like that. So you get more accuracy, you get more data throughput. So basically, if you're processing on 64-bit numbers, there's more data processing than you can do than if you're processing on 8-bit numbers. Now we're not going to go into architecture, but roughly that's what data path bit width means. Now there's a limit. I mean, you don't need excessive accuracy in your average system, right? So an 8-bit microcontroller, like the Arduino that we're using, is based on an 8-bit microcontroller. That is sufficient. That is minimal, but that is sufficient for the task that we're doing in this class, right? We don't need high accuracy, right? We're just doing simple control operations. We don't need accuracy in numbers. So it's a bit width is something you have to think about depending on the task that you're performing. Input-output pins. Now, this is actually an important thing because it's often a bottleneck. So you got your microcontroller. The microcontroller is the center of the system. It's connected to everything. It's orchestrating the whole system, right? So the microcontroller has to connect to all the different components that you want to put in your system. Now, maybe not all, but to a lot of them, okay? And it requires pins to connect it to these things. So maybe you need 3 pins to connect to one integrated circuit, and 5 pins to connect to another, and so on, depending on what the circuit is, how many pins it has on its interface. And you can easily chew up all the pins. You can easily use up all the pins in a microcontroller because these microcontrollers generally they don't have too many pins. So you have to be careful about how you use the pins. So that's why very early in the design process, you have to sketch out your design, figure out what the different components are you going to use, and how many pins each one of them needs to talk to the microcontroller. And so you can get a number like say, okay, I need 40 pins, and then you can find a data sheet that reports it has at least 40 pins and so on. Right? So input-output pins are important for that reason. Performance, okay, so performance is important. It depends on the application, right? So sometimes it's important, sometimes it's not. Now, one thing to note with performance is many times when you're making an IoT device, it's interacting with a human, right? It's a device that's dealing with a human, and humans are slow. So humans, they don't need you to respond too quickly. Now, when I say not too quickly, let's say you're putting images on a screen. These images on a screen, if you put 30 a second on a screen, a human will be very happy with that. A human will see it move, everything will be smooth, right? Now, 30 things a second, operation a second is very little for many processors, and it depends on the processor. But that's maybe the processor could do a lot more than that, but it's not necessary because the human is slow. So you especially get with sound, right? With audio, a human can only hear 22 kilohertz, I think, is the maximum frequency. That is not very fast. Okay, 22,000 operations a second. It's not that's not a high rate of processor speed, right? So a processor can process audio data much faster than a human can hear the data, right? So you can use a pretty slow processor and still produce satisfactory audio. So performance is important. You have to consider that. Depends on your application. Video requires a lot more. Even though it's 30 frames a second, each frame might have many millions of pixels, and you might have to do lots of processing on that. So video generally requires a higher rate, but audio, if you're just doing audio or tactile, maybe somebody's pressing a button, something like that, very slow clock rate is sufficient. There we go. Okay, so some other features. Timers. There are other components inside your microcontroller that are commonly useful to an IoT system, like a timer. Now, it is you need a timer for any type of real-time application, and a lot of IoT systems have real-time functionality in them. So, say you want something to happen at a certain deadline. I want to sample this sound at every 1,000th of a second. I want to sample the sound. Then you need a timer to trigger that event to happen at that rate, right? So, or I want to sample a monitor. I want to sample some temperature monitor at some regular period, right? You need a timer to set that to force it to happen at that rate. So timers are really important in microcontrollers. So you need a few timers. And when you're considering the timers, there's a timer accuracy issue. You got to think how much accuracy do you need in the timing, and then that determines the bit width of the timer, right? So an 8-bit timer is less accurate than a 16-bit timer. We'll get to that later when we deal with timers. But anyway, timers are components that you look for. You always want a few of them in a microcontroller. Analog to digital converters. So what this is for is to read analog signals. Now, the issue here is that microcontrollers are generally digital devices. Okay, and when I say digital, all the numbers are zeros and one, off or on. They're discrete values. Okay, 0 or 1, nothing in between. Now, analog is it's a continuous set of values. So the difference between analog and digital is the same as the difference between real numbers and integers. Right? They're discrete integers. You can have 0, 1, 2, but you can't have 1.5. Where analog is continuous. You can have any number anywhere. Now, microcontrollers and integrated circuits in general, they are almost always digital, completely digital, because it's much easier to design a digital circuit than it is to design an analog circuit. But they're digital. But the world is analog. So what I mean by that, say this light that is in my face while we're recording. Right? This light can be a little brighter. I hope it's not a little brighter, a little dimmer. Okay, it's not just off or on. They can increase the brightness, decrease it in an analog way. So phenomena that humans interact with, sound, right? I can talk a little louder, I can talk a little softer, and so on. So that's an analog phenomenon. So the world is generally analog to the perceptions of a human, but these computers are digital. So if you want an IoT device to process these analog phenomena, it has to convert it into a digital number. So the brightness of this light. Say I want my IoT system to do something with when the brightness reaches a certain threshold. It needs to be able to take that analog value of that light brightness, convert it to a digital number that I can use in my code. I can say if brightness is greater than 1,000 or some digital number, right? So analog to digital converters are important in IoT devices because you want it generally, it's very common to take analog phenomena and convert it to digital values that you can process in your code. So A to D converter, analog to digital, A to D, usually want one or more of these in a microcontroller. And I'll note right now, Raspberry Pi does not actually have an analog to digital converter, so that limits it in certain ways, but it's very common for a microcontroller to have at least one analog to digital converter. Low power modes. These are common nowadays too. When I say nowadays, I'm an old guy, so I remember back in the old days when nobody cared about power. There's plenty of power. That's because everything was, things weren't battery powered. Everything was plugged into a wall. Also, microcontrollers were just much lower than, so they didn't consume much power. But nowadays, things are battery driven. Things are fast, right? The clock rate is fast, and the faster it runs, the more power it uses. So power is a very big issue these days when you're doing integrated circuit design and system design. So in integrated circuits, it is very common to have low power modes. In microcontrollers, you can have different low power modes. So the chip doesn't have to be just completely off or completely on. It can have these intermediate modes where certain things are turned on, certain things are turned off, or maybe something is turned on but it's running at a slower rate. Things like this. Maybe you can't use the memory, but it doesn't lose what it's storing, right? So it's got this intermediate state. So there are low power modes built into these microcontrollers commonly, and we're not going to cover that in this class because that's a little more sophisticated than we touch on in this class. But more advanced IoT systems, yeah, you're considering low power mode. These things often run off of batteries. You want them to run a long time and not suck down the whole battery, so that you often want them to run in low power mode when it's possible. So you can see this in the data sheet. You can write the front page probably. It'll say that it has certain low power modes. Communication protocol support. So what this is, and we'll get to this more later, but these microcontrollers, they have to communicate with other integrated circuits, okay? And these integrated circuits, the way that they communicate, they use some kind of communication protocol. A relatively simple communication protocol. The way that they send data to and from each other over a set of pins, it got to be in a certain order with a certain timing and so on. That's the protocol. And we'll get into more detail about these protocols later, but some of them are UART, I2C, SPI. Those are some, actually we'll cover those later in class. But these are protocols that you can look in the data sheet and say, yes, it supports I2C, yes, it supports SPI, yes, it supports UART, right? Now this is important because when you're making your bigger system, say you know you want your microcontroller to talk to some SRAM chip, right? This SRAM chip, maybe it talks I2C, but it doesn't talk SPI. If your microcontroller doesn't support I2C, then you have trouble. Now generally, these microcontrollers nowadays, they mostly support everything, all the ones I just said, and others too. So generally, you have, in most basic microcontrollers, you have a lot of communication protocol support, but you should check just in case. Thank you.
Okay. Okay. Okay, we will continue next time. See ya.